Double integrals over general regions. This is the second video. We're going to talk about center of mass. I'll show you how to figure out center of mass of a two-dimensional object. Could be a thin plate where density varies with position, varies with x and y, not with depth. If it varied with depth, then we would have to do a solid three-dimensional triple integral. But it just varies with two dimensions here. So to find the x-coordinate of the center of mass, we simply integrate x rho dA. This is a small little element of mass. dA could be dy dx or dx dy. And we weight x with mass of a small little rectangular element. And then we divide by integral of rho dA. That is the mass. This quantity here is also called the first moment about the y-axis. X actually gives you the distance to the y-axis, and that's why we call it m sub y when you integrate x. That's just the name for it. Y-coordinate, we just integrate y dm, and we divide by integral of dm. So, and that gives you the y-coordinate. It's a very easy formula to remember. You could mentally think of yourself as canceling out dA, canceling out rho, cancel out the integral symbols, cancel out. This r is just the name for the region R. It'd be a totally bogus math, but a good device to remember the formula. The only thing different about the numerator is an x stuck in here and a y stuck in here. So let's go about figuring out the center of mass. We're returning to this region here we talked about last time. And we have a density xy. The density is jointly proportional to both the x and the y coordinate. As x grows, the density grows. As y grows, the density grows. Down, up, right over here, it'd be 125 kilograms per square meter. That was what the density would be. Here it'd be 0. Here it'd be 5 kilograms per square meter, et cetera, et cetera. Well, first of all, let's find the mass. We need the mass for both parts. So the mass is going to be a double integral, density xy. You can do it dy dx or dx dy, it doesn't matter. X is going to go from 0 to 5, and y is going to go from 0 to 5x. And that matches up with this. dA is dy dx. So we're going to integrate xy dy. We get integral 0 to 5, xy squared over 2 from 0 to 5x dx. And now we have to plug 5x in and 0. Plug 5x in, gives you 25x squared. So this half, you can bring the half out front if you don't like dealing with the fractions. And then 25x squared times x, 25x cubed dx. And then we get 1/2 times 25x to the 4th over 4 from 0 to 5. And you can bring the 4 out. We get 25 over 8. And then 5 to the 4th power. And 5 to the 4th power is 625, so you get 25 over 8 times 625. And that's mass, that's going to be kilograms. That's a pretty large number. Let me grab my calculator down here. 25 times 625 equals divided by 8 equals, yeah, we'll leave it in fraction form. We got 15 625 over 8 kilograms. Okay, and let's write that off to the side here so we have it. We have the mass is 15 625 over 8 kilograms. We'll save that. Now let's find x bar. There's nothing symmetric about this. Actually, if this was a symmetric triangle, or if this was a square, for instance, x bar and y bar would be the same, but this isn't necessarily symmetric, so we can't assume that. Let's find f sub y is going to be double integral of x times density xy dy dx, same limits, x goes from 0 to 5, y goes from 0 to 5x. And that's going to be equal, we have an x squared here, but first we integrate y dy, so we have integral 0 to 5, x squared, y squared over 2 from 0 to 5x dx. Okay. And integral 0 to 5 x squared. We can move the 1/2 out front if you want. And then 25x squared. Actually, you can put 25 here if you want. X squared dx. Okay, I think that's all right so far. Well, this is x to the 4th. And so we have 25 over 2. X to the 5th over 5 from 0 to 5. And let's see, that's so you can divide 5 into that. It actually gives you 5 halves, 5 to the 5th power. Which, let's see what we get for that. 5 5 equals 3125. I guess we have that 5 there times 5. That's 15,625 over 2. So that's what m sub y is. Let me clear a little space here. M sub y is 15,625 over 2. Now, if you want units on this, keep in mind, let's have a look at this. This is kilograms per square meter. This is square meters, and this is meter right here for x. So the meters squared cancel. Yeah, and then we have kilogram meter. That's the units on here. So that is our second part. We can do calculations at the end after we do all these moment calculations. And then let's calculate m sub x. And we have to integrate y, xy, dy dx. And x goes from 0 to 5, y goes from 0 to 5x. And we have xy squared. Y squared dy is really what we integrate. So we're going to integrate 0 to 5, x y cubed over 3 from 0 to 5x dx equals, and let's see, plug in 5 cubed is 125 over 3. Let's bring that out front. And then we had x cubed times x is x to the 4th dx. And we get 125 over 3, x to the 5th over 5 from 0 to 5. And you can simplify that. 5 goes into that 25 times. and we get 25 thirds times 5 to the 5th power. That's a pretty big number. 25 times 5 to the 5th. And we got 78 125 over 3. That is our m sub x. And that's going to be kilogram meters. Now we can do some simple calculations. X bar is equal to m sub y over m. Keep in mind there was that switch there. It's not m sub x over m. M sub y is divided by 15,625 over 8. And now the units here, these are kilogram meters over kilograms. And so 4 meters, we assumed this was meters. It's right here. There's 5. And it kind of makes sense that it's over here because it's the density is growing with x, jointly with x and y. There's more y up here. And of course, so we expect it to be over here. The y coordinate, better be up here somewhere. So y bar is equal to m sub x over m. M sub x is equal to 78 125 over 3 divided by the mass, which in this case is 15,625 over 8, and this is going to be meters. This is actually just a factor of 5 right here in disguise. This was an extra power of 5, so you can move the 8 up here with a 5, and we get 5 times 8 over 3, which is 13.3. So it's not so much up here. It's actually is 25. It's about halfway in between here. So the center of mass is right about here. Now it's interesting. It's more dense up here than it is down here, but we have more area down here. So that kind of balances that out, I guess. If this were a rectangle, then it would be skewed more up here if we had equal area down here versus up there. So that's where our center of mass is. What good is this center of mass? Well, it's pretty important. Awful lot of Newtonian mechanics having to do with motion. If this thing is flying through space without any external forces, this center of mass will follow a smooth path. This thing may be wobbling every which way. It's the center of mass that follows the smooth path. Second of all, if you were to turn this object on its side, you could balance it on a pencil right there and spin it, and there wouldn't be any wobble. Okay, if you move it, it's going to be a lot of wobble, a lot of vibration, pretty important if you have an engine, for instance. You want to minimize vibration. So that's center of mass, x and y coordinate. Pretty good application of multiple integration. Will work into the fray. Eventually we'll talk about moment of inertia in a subsequent problem set. That's pretty useful for studying rotational dynamics. We'll work that into here. It's not that difficult in here because we're not doing all the dynamics with it, but it's pretty important. We'll be back with one more video. We'll actually start with a double integral, switch the order of integration. I'll show you how to do that. And that'll be the third video for this section.